I've recently returned from a long-haul flight, and as I came back through airport security where my hand luggage got scanned and displayed on a monitor, I thought that would be a pretty neat idea for an escape room puzzle. So I made my own X-ray scanner. You place an item in the slot at the bottom here, like this rucksack, and it gets scanned and the contents displayed on the monitor above. Now this could be an item of luggage, like one of these bags. Obviously you get to see different contents that they have inside them. But this could also be an alien artifact, a case of secret documents, or whatever the hell that is. Basically any sealed object that players can't open but need to be able to identify its contents. Now, obviously this isn't a real X-ray. It's a fake prop that simply detects which item has been placed in the slot and displays a corresponding predefined image on the screen. But it's still a pretty great escape room prop, and in this video I'm going to show you how you can make your own. So there are three main components used in this project, and if I just lift this panel off the bottom I can show them to you. So we've got an ESP32 microcontroller that's running the code. We've got an RFID reader, which is how we detect which object has been placed in the scanner. And then there's a Sprite media player, which displays the corresponding image or video file on the monitor. Now, I've used RFID in loads of projects, and that's the technology used in lots of escape rooms whenever you need to identify whether a player has placed a particular item in a certain spot. But not all RFID are created equal. You might be familiar with these MFRC 522 readers, which use the ISO 14443 protocol. Now, these are designed for use with access cards or fobs that are pressed right against the reader. So they only have a read range of a few centimeters. Now, if you've followed my channel for a while, you'll know that my normal go-to reader is a PN5180 reader. Now, this uses a slightly different protocol. It's the ISO 15693 protocol, and that's defined as a vicinity sensor rather than a proximity sensor. That means that the read range is greater. You can normally read a tag at a distance of about 20 to 30 centimeters from the reader. But here I'm using an ultra high frequency ISO 18000 reader. Now this is designed for reading electronic product codes or EPCs, such as inventory management in warehouses. So this read range is measured in meters. Now the exact distance depends on the antenna you use. Here I'm using a ceramic antenna that's about 6 centimeters by 6 centimeters, and that gives a read range of somewhere about 60 centimeters, slightly reduced because I've got it mounted under that board. But the other thing is you don't have to have the tag lined up directly in front of the sensor. It can actually be positioned at an angle off to the side. So what this means is that for every item that I want to be able to scan, all I need to do is to take one of these EPC tags and attach it somewhere to the object. So for these rucksacks, what I did was I actually just dropped the tag inside this zip pocket at the end, zip that up. And I don't need to be that precise about exactly where the tag is attached to the object, so I don't need to be. So long as it's in approximately the right place, I can then place it inside the scanner. The ESP32 will read the unique ID of that tag from the reader and then tell the Sprite to display the appropriate file. And same with the cardboard box here. So this has obviously got a different tag inside it, and I can place that there. And the ID associated with this tag, which I've got just floating around the box there, displays a different image file. So this reader is a lot more tolerant, and you have to be a lot less precise than you might be used to with these kind of RFID readers, where you typically need to place the item very specifically right in front of the reader to get these to register. This is a lot more forgiving, and that means it's a lot easier to create one of these kind of puzzles where players can just toss an item in and get it recognised. This is the exact RFID reader I'm using, which is an R200 board made by a company called Inverton. It is more expensive than those other RFID boards I showed. The board itself costs about £30, but then you also need to buy a suitable antenna. Now, the bigger the antenna, the longer the read range, but also the more expensive. However, it is pretty easy to use. Unlike the MFRC 522 or the PN 5180 boards that have SPI interfaces, the R200 reader here has a UART serial interface. That means you don't need to write much code or use complicated libraries to access low-level scanning functions. Instead, you simply write a command over the serial connection to instruct the reader to read any tags in range, and if it can, it returns their IDs via that same serial interface. Now, the board requires a 5-volt power supply, ground, and then just a single transmit and receive data line, and they can run at either 3.3 volt or 5 volt logic. So that means this can be used with almost any controller, an Arduino, an ESP, Raspberry Pi, or controlled directly from a PC. Now, having received the ID of any tags in range from the reader, the code running on the controller here then needs to perform some action based on the code received. And in this case, what I'm doing is to send a command to a media player to display the appropriate image file. And the media player I'm using is something called a Sprite. Now, these are very popular in the escape room world, as well as being used in museums, galleries, haunted houses, and other attractions. I actually found them a little tricky to get hold of in the UK, but I did find a distributor called Garland Digital, which is where I got this from. It cost about £100, which is more expensive than some other media players, but the main feature it offers is a lot of control over playback. So you place video or audio files onto an SD card or a USB stick, and then you can specify which one to play back in a couple of different ways. You can use a simple trigger like a button to start or stop playback, or you can have several buttons, each one linked to different video files. Or you can use a programmable serial interface. Now, because I'm controlling the file to play from code, I'll be using that serial interface. So I've got it wired to a transmit and receive line back to my controller and also to ground. And then I've got the HDMI output from the Sprite wired to the monitor at the top. And the final component I'm using is the ESP32 microcontroller here that's controlling everything. Now, ESP32s are very powerful little devices, but I'm hardly actually using any of its processing power at all. All the hard work of interfacing to the RFID card is being done by the R200 controller, and all the video playback is being managed by the Sprite. So all the controller needs to do is to send and receive commands to these other two devices. In terms of the raw processing required, you could probably replace this with a very basic Arduino Nano instead. But remember, I mentioned that both the RFID reader and also the Sprite used serial interfaces, and most Arduinos only have a single hardware serial UART. Now, an ESP32 has 3 hardware UARTs, and I can connect to both of these and also have one left over to connect to my PC via a USB cable for monitoring the code. Now, of course, you could also use an Arduino Mega, which has got 4 serial ports, or another microcontroller, or use software emulation for these other serial connections. But the ESP32 is such a great little device, and it's not expensive either, so that's the reason for choosing that controller for this project. And this is just a diagram to illustrate that same wiring that I've just shown you. So I've got my R200 RFID reader that is connected to my ESP32. We've got the transmit and the receive serial lines, which are connected to GPIO pins 16 and 17. We've also got ground connected, And you'll notice that there is a 3.3 volt pin here, which I'm not using because I found that that didn't provide enough power to the unit. Instead, there's a 5 volt pin at the top here, and I've got that connected to the V-in pin of the ESP32. Then on this side, I've got my Sprite player. That has its own power supply, which goes into the DC jack socket here, which I've not shown on the diagram. It then has the HDMI connector through to the monitor. And then it has a multi-purpose input-output socket here. So the way that this is wired depends on exactly what trigger mode you're using. If you're using a simple button input, that just goes in here. If you're using the programmatic interface, as I am, you use this little TRRS adapter that comes provided with the Sprite, and it's got screw terminals on the bottom here that I've connected to ground, and again to transmit and receive data line, for which I'm using GPIO pins 26 and 27 on the ESP32. The last terminal here, this is actually because you can use the power supply from the Sprite to provide power to another device as well, but I've not got that connected. You don't need to use that if you're powering the ESP32 from a separate power supply. The only other thing to mention is that you don't have to use the same GPIO pins as I have done here. Unlike an Arduino, which has dedicated pins that have to be used for the hardware serial interface, on an ESP32 it's actually possible to remap any available GPIO pins to use its 3 serial interfaces. I've just used these ones because they were conveniently located on the board, but if you want, you can assign those to any other pairs of GPIO pins you want. The only thing you need to do is to modify the code accordingly, which I will now show you. So here is the code. It's not that long, so we'll simply step through it line by line together. It starts at the top by including this header file here. Now, I said that one of the benefits of the R200 reader is that it didn't need any external libraries. And indeed, this is not an external library. This is actually a header file which I've defined locally in the project here. And all I'm using this for is to separate out some of the control codes that are used by the RFID reader, just to clear up the main body of the code here. Now, I should say that the vast majority of these we're not even going to use. So the RFID reader has the ability to write tags as well. It has the ability to automatically hop onto different frequencies, or to record the signal strength of the connection, things like that. We're not going to use hardly any of this. I think we're only going to use a handful of these instructions to poll the card and read the label that it gives back. But I thought, bearing in mind I was writing this functionality for the RFID reader anyway, I may as well include those functions now, just in case you want to use them in the future. It also does things like checking the checksum return to make sure that the value returned from the reader was valid as well. So I'm just including that at the top of the code, but this is not a library that you're going to find in the Arduino library manager or anything like that. This is just a local file in the project here. Then I define a structure, and the point of this structure is to associate a file number on the SD card of the Sprite player, so which video file to play, with the ID or an RFID tag that's been scanned. Now, the EPC codes that we read with this reader are generally 12 bytes long. Some other formats of RFID cards only use 8-byte IDs, but this is generally 12 bytes. So the first element of this structure is a 12-byte array, which we'll call UID. And the second element is a single byte value, which is the file number of the media file to play. So on the Sprite player, you save your video or image or audio files with index numbers. So 000.mp4 is your first video file, and then 001, 002, 003, etc. And to trigger one of those to play, you simply send the single byte value corresponding to that index number. So if you want to play the file that is saved as 003.mp4, you send the byte value 3 to the Sprite player. 000.mp4 is a special case. That's kind of the default background looping video. So in my case, that's what I've just had set to a blank screen, and that's what I'm going to display when no RFID card has been recognized in range. So that's just the structure that defines the connection between those two things. We actually populate those values in the next section of constants. So we're going to define 3 different images that we can display on the monitor. We've got 3 different objects that the players can scan. And this is an array of those 3 values, and each one of them is going to contain one of these scan image structures. So the first 12 bytes from here to here, this represents the EPC code of an RFID card which can be scanned. And if that is the EPC code that is recognized, this is the video file index that we're going to tell the Sprite player to play. So I've got my 3 video files, 001.mp4, 002.mp4 and 003.mp4. Those correspond to the 3 images of rucksacks and boxes which I showed you on the monitor. And then I've also got 000.mp4, that's my background image. This is the EPC code of the 3 different tags which I attach to the objects. And if you want to know what the EPC code of a particular card or fob is, you can simply scan them using this code, and a bit later on in the loop function, when I get to show you that, you'll see there's a value here called RFID.UID. If you simply add a serial.print command into the function here and print this value, you'll be able to see what the ID associated with any card is. Then you can add that onto the array here. So you can have as many elements in this array as you want, each associated with a different video file. Then we get onto the global section. So this is where we define some variables that are going to be shared among the whole code. And we are going to define a hardware serial connection to the Sprite. Remember that I said the point of using the ESP32 is that it has 3 UART ports. So we're going to be using UART1 for our Sprite controller. We're going to be declaring an instance of the R200 class, and although we don't actually specify it in the constructor here, that will be using the second UART interface. And then we also just define 2 variables that we're going to use to keep track of the RFID tags that we've scanned. So first of all, we're going to define a time variable. It's just the timestamp when we last looked to see if any RFID tags was in range. Now, if you wanted to, you could only manually activate the scanner. So players would actually have to physically press a button, and when they did so, it would scan to see if anything was in range. Or you could have it automatically check every millisecond or every second, however often it is. And the scan time variable here is just to keep track of when was the last time we saw whether any tags are in range or not. And if greater than a certain duration has elapsed since that time, we'll conduct another scan. So it's to poll at regular intervals. And this keeps track of the ID of any tag that was present last time we scanned, just so we can tell whether a new tag has been inserted or whether one has been removed, or whether it's just the same as last time. So we'll just keep a track of that there. Now we've got 2 helper functions. So the first one here, this displays an image on the Sprite media player based on the corresponding UID that was scanned by an RFID reader. So as I mentioned, the default value is going to be 0.00. That's our default video file that's going to play on the monitor if nothing else has been recognized. And what we'll do instead is we'll loop over all of the images in our scan images array, which is what we defined up here. We'll check over all the values here. We know that there are num images of them, so there are 3 of them. And for each one, we'll compare the UID that's in that array to the UID that was supplied to this function. And if it matches, which means that memcomp returns 0, then we will set the output value to the file number corresponding to that element of the array. So we'll loop over all of them, see if any of them is a match, and if they are, we'll replace output with the corresponding file number. If none of them match, so if we get to the end of this loop and none of them match, then output is still going to equal its default value of 0. And then what we'll do is we will write that output index file to the Sprite controller, which was using the first UART interface. So this is going to write a single byte to the serial interface of the Sprite controller, which is either going to play the 000.mp4 file, which is the default, or if a matching video file was found for the ID card that was scanned up here, then it will play whichever one of these index files was found instead. So that's that function there. And then we also have a Sprite loop function. Now, this is not actually required, but I included it deliberately just to show you how you can read data from the Sprite as well. Generally speaking, in this project, we're just writing data to the Sprite. We're using it as an output, and we're telling it to play this file or play this file or this file. And you sort of think, well, what data could we possibly receive back from a media player? And the most useful value you can receive back is a byte here, this hexadecimal value EE, and that is what the Sprite returns to the controller when a video stops playback. So when it reaches the end of the time for it to play back, it returns this value. And what do you want to do when that happens? Well, in this case, we want to restart the video that we were playing previously. We basically want to make it continuously loop unless we have an explicit reason to stop the video. We just want to loop the video over and over. So that's what this function here does. We call this on each iteration of loop. And if the Sprite controller has sent back some data to the serial connection, we'll read it into a single byte value here. If that value is this special code here, which is what the Sprite player sends back when a video is finished, we'll just simply tell it to play again. Now, I will just mention at this point as well, in the Sprite best practice guide, one thing it recommends is that you should save your video files as long video files as you can for the size of SD card you're using, really. And the reason for that is it will actually make your media last longer. SD cards, when you have a very short media file, let's say your media file is only a second or 3 seconds long, if you were to loop over that same very short video over and over again, you're constantly reading the same blocks of data on the SD card, and effectively you wear them out. Whereas if you were having a video that is 3 minutes or 10 minutes long and you're playing it, although it will look the same on the screen to the player, you're actually reading new bytes of data from the disk, you're reading new blocks, and you're spreading the wear on the SD card over a much larger number of blocks. So generally speaking, you don't want to have short video files that loop over and over like this. It's much better practice to have a much longer single file that just plays a looping video, as it were, although the file itself is not looping. But I thought I'd just include that. Like I say, that's not actually required, but I wanted to include the functionality of how you can read data sent back from the Sprite and act upon it. And then we go on to the setup function that runs when the code first fires up. And this essentially does nothing other than configure the 3 UART serial interfaces that we're using. So the first one here, this is for UART 0. And this, as is very commonly used, is what we're going to use to monitor the code remotely through the USB cable to our PC. So we'll set up the serial connection at a baud rate of 115K. We'll print the name of this sketch and the date at which it was compiled. And having done that, from now on, anywhere in the code that we want to debug the value of a variable or something like that, we can call serial.print, and it will use this serial interface. We then set up the next serial interface. So this is using serial 1, our second UART, and this is going to be the one that we use to interact with the Sprite player. So as I mentioned when I was showing the wiring diagram, you can use any GPIO pins for this. I'm using GPIO 26 as the transmit line and 27 as the receive line. And I'm using a baud rate of 9600, which is the default baud rate for the Sprite controller. But if you want to set that to a different pair of GPIO pins, that's fine. You just need to update these values here. And then we're going to configure our third UART serial interface. So this is using UART 2, which is the one that we're using to the RFID reader. And just as before, we're going to set a baud rate, but this time I'm using 115200, the same as I was for my connection to the PC. That's the default baud rate for the R200 reader. And I'm using pins 16 and 17. But again, you can change those if you want to. I'm then just going to send a couple of commands to the R200. The first one I'm going to do is dump module info. This will just print some information to the serial monitor about the firmware version that's running on the RFID reader. And I'm also going to do something called automatic polling, which I'm going to turn off. Now, a little bit earlier when I was talking about the last scan time here, and I said we were going to, you could either manually trigger the RFID reader to scan any tags in range by pressing a button, or you could poll it every second or 2 seconds, however long you wanted on a schedule. It does have an automatic polling mode here, which basically continually polls as quickly as the reader is able to. And I've turned that off and have decided to use a manual polling method instead. And the reason for that is there is a buzzer attached to the RFID reader. And by default, the buzzer makes a bleeping noise every time an RFID tag is scanned. Now, if you wanted to use this reader for some sort of inventory tracking, management, checking out books in a library or security tag or anything like that, that would be a feature you'd want to keep, because obviously you have the beep to detect when a scan had positively been recognized. For an escape room setting, what we're generally trying to use RFID tags for is to provide a mystical, hidden smoke and mirrors way of detecting whether an object has been detected or not. If you're in an Egyptian tomb and you've just placed some canopic jars representing, whatever it is, or an offering to the gods, you don't really want a beep to accompany placing the item in place. It rather ruins the suspension of disbelief. So I've turned that off because I didn't want to have the continual beeping going off every time the RFID reader scans a tag. Now, of course, I could have done that another way. I could have disabled the buzzer. I could have just put a bit of tape over the buzzer. But what I've done instead is I've turned off multiple polling mode just so I don't get that constant beeping. And instead what we'll do is we will manually poll the sensor, which is what we're going to do in the loop function. So in this case, I'm polling every 2 seconds. And if more time has elapsed from the last time we scanned than 2000 milliseconds, so 2 seconds, we will poll the sensor to see if any tags have been read, and we'll update the value. You may have noticed in the video demonstration there was a slight sort of delay, so the image on the screen remained for a couple of seconds after I took the item out of the slot, and also it takes a little while to first reveal it. This is the reason why, because I'm actually only updating that image every 2 seconds. Now, I quite like that. I like the idea that an X-ray machine would actually take a moment to scan and give you the result, and persists a little while after you remove the item as well. But if you wanted something a little bit more responsive, you could obviously change this value up or down as you see fit. On every iteration of loop, we also call this function here because this is what's going to check whether anything has been returned from the sensor. So this is like sending the command to the sensor, telling it to detect if anything is in range, and then this function here is to read the response. And having done that, what we need to do is to see whether we've got anything in that response. So we compare the ID that was read from the RFID reader last time we called loop. We compare it to the value of the last time we called it, which, remember, at the top of our code here, we defined a global variable here, which is a 12-byte value. That's the last user ID we know about. If we compare the current one to the previous one and there are any differences, then what we need to do is we update our stored value to reflect the current one, and we need to display the image on our Sprite media player corresponding to the newly read value. Now, as I mentioned earlier, when you first set this puzzle up and you need to populate this array here with the ID values of all the tags that you are reading, this is the section here where you could add serial.print command, and if you print this value here, you could then scan all your cards in order and get the IDs associated with each one to be able to populate that array. And finally, what we do is we call the Sprite loop function. I already showed you what that did. That was the one that if the sprite gets to the end of a video file, it will simply cause it to loop over and over back to where it started from again. And that's the end of the code. Now, I mentioned that I turned off the RFID reader's automatic polling mode because that made a continuous beeping sound every time an RFID tag was in range. Now, I didn't want that for my X-ray scanner, but it does come in very useful to demonstrate the detection range of the reader. So here I've uploaded the code again, but with multiple polling mode set to true. I've also taken away the extra hardware for now, so you can just concentrate on the RFID reader itself. And I can take this card and pass it over the reader, and that beep shows the ID can be read quite a long way around the reader. It doesn't need to be precisely positioned directly in front of the sensor. In fact, I can even place it off to the side, level with the antenna. I can spin the card over and lift it up. That's actually gone off the top of the camera, hasn't it? Let me bring it slowly back down. So I'm about a metre above the reader here, and I can bring the card all the way down. Spin it round. It loses contact a bit if it's exactly at right angles, but hopefully you can see that this is significantly more robust detection than most common RFID readers you might have seen. Now, the opportunities to use an airport-style X-ray scanner like this are limited to a fairly specific set of escape room scenarios, but even if you don't want to create this exact prop, I hope that in this video I've been able to explain two very useful pieces of hardware, the Sprite media player and the R200 RFID reader, which can be used either independently or together, as I have done here, in a whole range of different escape room props. Now, as always, I will upload the code that I demonstrated and also a copy of the wiring diagram and other resources over to my Patreon account, which I will link below. I'm only able to create these tutorial videos each month with the support of my Patreon donors, and I want to say thank you all ever so much for your ongoing support. I really appreciate it. And if you go over to my Patreon, you'll be able to find details of all the escape room projects I've ever created in this channel. If you are unable to support me or don't want to, that's fine. I will keep on uploading these tutorial projects to YouTube each month anyway. And you can always ask any questions or comments or suggestions down below, and I will do my best to get back to you. Other than that, I just want to say thank you all very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.